Welcome to everyone. I'm Aniello Mungiello from the University of Naples Federico II, and I will present a paper that I did during my research period abroad at the TUM University. The title is Model Structured Neural Networks to Control the Steering Dynamics of Autonomous Race Cars. First of all, let's start with the motivation around this work. As we know, autonomous driving is one of the most popular research topics nowadays. In fact, researchers try to address the tasks for the vehicle autonomy, but they still centers on a hybrid scenario, where usually they avoid safety critical conditions that can occur near dynamics limits. For this reason, to address this gap, autonomous racing has emerged as a benchmark for advancing perception, planning, and control. In this situation, in fact, the vehicle drives near the limits of handling, where the vehicle dynamics become highly nonlinear and sensitive to tires, suspension, and aerodynamics. The case study of this work is the autonomous racing car of TUM that competes in the Abu Dhabi Autonomous Racing League, where the vehicle drives at the Yas Marina circuit, reaching speeds over 200 kilometers per hour. To capture these dynamics, researchers presented three main approaches: physics-based modeling, general neural networks, and model structured neural networks. The first one has the advantages of the interpretability of each parameter inside the model. However, these advantages come to the cost of the computational burden. The more complex the model becomes, the greater is the computational demands, and this could be a problem. For this reason, usually you need to neglect some aspects. While approaching with the general neural network, you can consider the entire phenomena, but at the cost of the interpretability and the scalability of the scheme, as well as you need a huge amount of data to train the entire network. For this reason, the last approaches has the objective to identify an optimal trade-off between the two previously discussed approaches, aiming to balance the interpretability and the robustness. In this work, we want to contribute introducing a novel model structured neural network capable of control the steering of an high-performance racing vehicle. The model is trained and validated on real data from the last year of the competition of the A2RL competition, and it is benchmarked against three references: the previous controller endued on the vehicles, a general purpose neural networks, and the baseline form of our extended version of the model structured neural networks. Finally, we release an open source code for generating a customized model structured neural network architectures and to perform the hyperparameter optimization. So, moving now to the steering control design, we will present a first overview of the entire autonomous stack. The design of the model structured neural network is both for the baseline version and extended version. Then we present the racetrack layout and the labs that you use for the data set generation. And finally, we will talk about the implementation of the model structured neural network and the hyperparameters unit. So the overview of the entire stack is composed of the trajectory planner that tries to compute the optimal trajectory in terms of future window, speeds, longitudinal acceleration, and lateral acceleration for the two controllers, for the longitudinal controller and for the lateral controller. In the lateral controller, we have two components, the feed-forward part and the feedback part. In this work, we are focusing only on the feed-forward part, designing a model structured neural network that computes from the window, future acceleration, longitudinal lateral acceleration, and longitudinal speed, a command of steering. The entire architecture can be divided in a quasi-steady state part and a transient dynamics part. The transient dynamics is composed of a fully connected layer and activation function. Exploiting the fuzzy logic, we linearize around the local model of longitudinal speed and lateral speed the function that comes from the steady state dynamics. Then, using the fully connected layer, we learn the linear combination of these models, computing only one component, one steering angle that we want to apply on our vehicles. While the quantitative state dynamics is designed focusing on the handling diagram. The handling diagram represents the non-linearities of understeering and oversteering characteristics. In fact, the handling diagram quantifies the mismatch between the real steering angle and the kinematic steering angle. So, to capture these dynamics, it is designed the function G, that is a function that can be linearized in a local model of lateral and longitudinal acceleration. This is the architecture and the function for the baseline version of the model structure in our network. But in this work, we want to present also an extended version. An extended version on the fact that, as we can see from the handling diagram, the curves, the slope of the curves can change respect to the speed range. So we want to add a component that can keep also this behavior. To do that, we use a polynomial degree for the first two learnable parameters that they becomes function of the speed, and the degree is settled through experimental testing. In this way, then we focused on the racetrack layout, and we use two pre-qualified laps. The second lap is used for the validation sets, while the first lap, is used for the training set. But this lap is divided in sector. In this way, we want also to quantify the generalization capability of our approaches respect to different amount of data in the training set. For this reason, we defined a small training set for if we focus only on the sector 3, a medium training set if you use the sector 3 and sector 1, and a large training set if we use the entire lab. For the implementation of our approach, we exploit the root mean square error with the Adam algorithm, and we implemented also the early stop techniques. As the hyperparameters, we set the learning rate as 10 over minus 3, 8,000 epochs at the batch size of 1,000. Finally, in our model, we need to define the correct number of local model, both for the transient dynamics and the quasi-steady state dynamics. To do that, we implement a code to try a tuning of these hyperparameters, changing the value of local model of lateral acceleration, longitudinal, the number of local model for lateral acceleration, longitudinal acceleration, and longitudinal speed, and also the future time window, the size of time window for future states of these components. And we change in a range these four values and compute the AKK information criteria, that is a metric that format selection, which trades off the model accuracy versus the complexity of the model, with a lower A value indicating a more simple, efficient models. So a trade-off between the accuracy of the model and the number of learnable parameters that we have in the architecture. Computing this value for each settings of parameters, we find that the best solution for our approach and for our implementation is the number of local model for the longitudinal speed and longitudinal acceleration of 3 local models, for the lateral acceleration of 5 local models, and the time window of future step of 10, achieving a number of learnable parameters of 160. Switching now to the benchmarks used in this paper, we used, first of all, a general purpose neural network. Firstly, we concatenate the same inputs of our model, and then we use two fully connected layers with an exponential linear unit activation function. The numbers of neurons in the first fully connected layer matches the number of learnable parameters that we have in our approach. The central benchmark is baseline HRL steering controller that is built on the vehicle in the last competition. This controller is composed of 4 components. The first one is the kinematic steering angle. The second one is to estimate the understeering behavior. The third one is a compensation term that accounts for the weight transfer and the aerodynamics effect. And the last one is an offset, a static offset defined during track tests. So, passing to the results, we can see from these two plots how our approach outperforms the other ones, both in the training set, with the training set and validation set. In fact, our approach shows a smoother steering profile, which favors vehicle stability and reduces the risk of dangerous oversteering situation. This is true also if we're focusing on the box plot of the steering angle errors, where we can see how our approach computes less value of outliers in both training situation and validation sets. Moreover, computing the metrics of root mean square error and fraction of variance explained that give us the possibility to quantify the portion of variance in the target data that remains unexplained by the model with a less value of a lower value of FU that indicates a better performances. We can see in the table how our model, both in training set and validation set, outperforms the other 3 benchmark used. Keep in mind that these implementation, these results are using the latest dataset. So for the training, so using the entire labs. Now we are focusing on the generalization performance of our approach and the benchmark respect to the use of a medium and a small training set. So using only part of track, only some sector. And we can see how we can demonstrate the better generalization capability of our approach. And this is a crucial aspect. We can see this in the table. This is a crucial aspect for real-world application, where collecting data can be expensive and time-consuming. And also, of course, the environmental may change over time. So you don't need to keep a lot of data to train the network in our approach. Finally, concluding, resuming all the presented paper and talk about future steps, we see in this paper a novel model to do a neural networks to control a full-scale autonomous race car, and we demonstrate the capability of interpretability of each parameters and the generalization capability of the result. We train it using real-world telemetry and demonstrate to outperforms all the benchmarks. Finally, for future work, we want to deploy the model structured neural networks on a real car in the ATRL competition, and we'll test it in closed loop when combined with the trajectory planners. Thanks for your attention.